we are now going to understand the placement aspect of on the topic of coverage and placement of wireless sensor networks. So, in the second part we are going to understand the problem of placement and the different solutions with respect to this problem. So, first of all, in the sensor placement problem, it is assumed that there is a perfect disk that is used for deployment, and that perfect disk assumption is usually made in which each sensor monitors a circular area that is centered at the sensor and with a radius of the sensing range r. And this particular thing, this particular concept we had covered in the previous part of this topic as well. There I spoke about not only the disks, but also the concept of unit disks. So, when we have a sensing range which is of value unity, then what we have is the unit disk. And so, we are typically in all these algorithms that are proposed in terms of coverage and so on and so forth, many of these they assume there is an existence of not only a perfect disk, that means it is completely circular in shape, but also with a particular radius r, but also that r is also unity, which gives a unit disk assumption, right. So, typically the unit disk assumption is made in these algorithms that are proposed. So, one of the most important and upfront issues in this particular context is where to place the sensors in order to fulfill certain performance criteria, right. So, placement problem. So, where to place the sensors in the particular area of interest, subject to certain constraints such as the number of sensors to be deployed, the distribution of the threats in the terrain, the land cover and meteorological conditions of that particular area of interest, or the population distribution, where you are going to place the different sensors under these different constraints. The problem considered is more realistic in three respects. So, first of all, we have to place the sensors so that the detection time is not negligible. We have to consider that the detection time is not negligible. So, we have to consider that there is a certain t duration of detection time. Detection time means that time that elapses from the point that the event occurs until the point that it gets detected, right, that is the detection time, and it is not negligible. Second is that allowing the sensing area of a sensor to be anisotropic and of arbitrary shape. See, typically the areas of deployment or the regions of deployment, they do not have a regular geometric shape, a circular shape, and so on. So, you have to assume that whatever sensor placement algorithm that you propose, it takes into consideration that the area of interest does not have a isotropic shape, a regular shape, it can have any arbitrary shape and so on. And the third is defining the utility function to model the expected risks of insufficient coverage. Utility function concept basically has been borrowed in the optimization literature from microeconomics. So, utility function means that by doing certain things, how much is the utility, right, how much is the utility to the users or the, let us say, customers and so on in certain scenarios. So, defining the utility function to model the expected risk. So, you have to define the utility function in such a way that the expected risks of insufficient coverage could be computed. So, when we are talking about a sensor placement problem, there are three different variables. Number one is the number of sensors to be deployed in the field of interest. Number two is the maximum detection time, and detection time is something that I already told you, that the time that elapses from the instant a particular event occurs to the instant, till the instant when that particular event is detected by at least a sensor node. So, that is the maximum detection time. So, N, T, and the third is the coverage requirement. So, what is the desirable coverage? C R E Q suffix. So, that one C R E Q is the coverage requirement. How much is the desired coverage? So, to incorporate the effect of propagation and dispersion nature of plumes or any other events and so on, the coverage area should now be a non-decreasing function of. So, coverage is a non-decreasing coverage area. That means that with time the area that is covered should not be a decreasing function at all. So, that means that either it is 0 or it increases, right. So, the longer the maximum allowable detection time, the larger the sensing area of a sensor node. So, there are three problems, analogous problems, that have to be considered when we are considering three variables N, capital T, capital N, capital T and C. So, the first variant of the problem is that given the number of sensors N and the maximum detection time T, how to place the sensor so that the coverage requirement C R E Q, for instance. So, in this particular slide we have C denoted, but to understand better we can think of it as C suffixed R E Q. So, C R E Q is maximized. The second variant of the problem talks about that given the number of sensors N and the coverage requirement C, how to place the sensor so that the maximum detection time is minimized, and given the maximum detection time T and the coverage requirement C, how to place the sensor so that the number of sensors capital N is minimized. So, three variants of the problem by keeping two of these variables constant and varying the other one, or maximizing or minimizing the other one. So, the problem equivalence is like this, that suppose we have a solution algorithm which maximizes the coverage given N and T to the first problem, then we can construct, using a binary search kind of approach, we can construct a solution algorithm minimize T given N and C to the second problem as follows. So, what it is saying is that given this, we can propose a solution algorithm which minimizes T given N C to the second problem in this way. So, a binary search kind of approach can be followed like this, that capital T is the entire duration of detection. So, in one end we have T min, the other end we have T max. So, this entire period T min to T max can be partitioned and you get the midpoint, let us say. So, you reduce the search space from T min to the middle of that search space, you reduce the search space to 50%, half of it, and then continue your search operation recursively as you do in the case of binary search. And I am sure that all of you who are listening to this lecture, you are familiar with the binary search algorithm, which is a very fundamental algorithm in computer science algorithms and so on, binary search algorithm. So, I am assuming that you know the binary search algorithm. If you do not, you will have to know little bit of basics of it, or even if you do not know, also probably from these statements you can understand that what binary search attempts to do. So, let T min and T max denote the minimum and maximum possible values of the detection time T. At the beginning we set T min equal to 0 and T max the time duration in which a sensor can cover the entire field of interest. So, we have the median to be denoted as capital T. Now, T becomes T equal to T min plus T max by 2. So, that means that the search space you have truncated to half of the previous one. Invoke the max C and T problem and compare the return coverage C0 against the required coverage C. So, how much coverage you are getting, you have to compare against what is the desirable coverage. Now this part is quite obvious, as it happens in the case of binary search. You follow a similar kind of approach. So, if C0 is equal to the required coverage C, then T is the optimal value. Otherwise, if C0 is greater than C, we continue the search in the time interval T min T. Otherwise, if C0 is less than C, we continue the search in the interval T T max. The search process terminates when one of the following two conditions is satisfied. That means, changing T does not result in change of C0, and T min minus T max, T max minus T min is less than a certain value, which is the minimum time that is required for the event to propagate through at least one cell. So, by a similar line of argument like what we have gone so far, we have covered so far, we can use that to minimize TMC to construct and the solution to the algorithm minimize n given Ct to the third problem, and use the minimize n given Ct to construct a solution algorithm for max Cnt to the first problem. So, basically, what it is saying is that by following the similar kind of approach, we can look at a solution for max Cnt problem. The third problem is bit different, and this formulation is bit different, and its analysis is bit different. So, we formulate the third problem by dividing the field of interest into a set X of cells. So, it is saying that this entire area is divided into a set of cells X. We assume that at most one sensor can be placed within each cell. Okay. So, at most one sensor, So, the entire region of interest you segment into different cells, and within each of these rectangular cells you place at most one sensor node. At most one sensor node you place in each cell, and if all the cells have at least a sensor node placed, the whole cell and the whole region is said to be covered. Now, let us look at this particular problem formulation for the third problem. So, now what we have is to minimize the number n, which is a summation of xi's of sensors subject to this particular condition given in equation 1, where u stands for the utility and R is basically the region that is covered by a sensor at particular time t. RIT stands for the covered region by a sensor at a particular time t, and xi is the number of sensors in the ith cell. The utility function quantifies the utility of covering an area in the field of interest. For example, the utility function can be population of an area, the probability that the targeted event that takes place in the area, or combinations thereof. Okay. So, now the motivations are that there are large amount of research activities have been undertaken in designing and analyzing protocols for sensor tasking. That means, scheduling the activities of these different sensors. Tracking, sensor tracking means that given the sensors which are deployed, how to track the trajectories of the targets that are moving in that sensor field. Localization means finding out the locations of the different targets, or even the locations of the different nodes in the network, and in network processing and communication. And there has been much less work that has been done in deploying sensor nodes, sensor networks. The limitations of the existing works are like this, that they assume that there is a perfect sensing area. That means, it is some sort of a perfect sensing area, means a completely circular area or some regular shape, and some kind of isotropic shape of the area, ignoring the detection time and assuming that there is fully geometric coverage. These are some of the limitations of these existing areas, existing works, and these limitations basically motivated the authors to come up with to do this perform this particular study, this analytical study. So, let us look at the problem formulation for the last part once again. So, let us assume that X is a set of cells. X is a set of what? Set of cells that the area is divided into, and it is divided. So, we have a rectangular shaped area, let us say you have divided into different cells. So, you have small rectangles, and within each of these you have to place these xi's. X subscript I is basically the ith sensor to be placed in a particular cell, xith sensor. Ri is the set of cells that can be covered in a particular duration of time by placing the sensor in the cell, and ui is the utility that is gained by covering the particular cell. The objective function is to minimize the summation of all these xi's, and there are two constraints. If we are talking about the one coverage problem, the constraint is like this, that utility of the union of all these Ri's that should be greater than or equal to C, which is the coverage requirement, and if it is a k coverage problem, the corresponding constraint equation is as shown. So, this is the corresponding coverage equation, and over here I is an indicator function. And what is an indicator function? This is a function that is defined on a set X that indicates the membership of an element in a subset A of X having the value of 1. So, this indicator function, so this part is important. So, this indicator function has a value of 1 if A is covered by at least k sensors and the value of, and it has a value of 0 if it is not, that means otherwise it has a value of 0. So, those discussions were to do with stationary sensors, but mobile sensors are also very useful, because spatiotemporally you can have better coverage by having lesser number of sensors if we are considering mobility of the different sensors, right. So, mobility can be useful to extend the coverage area over time without using more sensors and reacting to contingencies, example changes in the environment or sensor failures, and supplementing static sensors to fill in holes, coverage holes that might be existing, or facilitating communication between the different parts of the area. So, cost of mobility can be controlled in different ways. So, the control movement of the sensors, so it is required to control the movement of the sensors to achieve various coverage goals, and these coverage goals might be to discover new or interesting information through mobility, observing interesting events by staying in the network, or to be fair to different regions with different degrees. So, maybe being more giving more important regions more attention, and higher risk regions giving more attention, and so on. So, what is required is to minimize the travel overhead in terms of time and energy, and reduce the demand on the sensors. So, there is an algorithm, the WRP algorithm, which is a thread based mobile coverage algorithm that is proposed, and I am not going to go through it in detail, but just to give you a little bit of feeling of what it does. So, three different parameters are considered. One is the maximum trip length, the second one is the adaptivity to prior coverage, and the third one is the random pause time. So, three different criteria are considered, and a mobile coverage algorithm is proposed. So, how fast the sensor nodes are moving, how fast or how slow the sensor nodes are moving, whether they are moving continuously or not. So, these things basically have implications on the coverage using mobile sensor nodes, and so how long they are going to move, and then whether they are going to pause for certain duration of time. So, these things, so the pause time, mobility, etc., the rate of mobility, the speed of mobility of the different nodes, all these things have implications on the coverage using mobile sensor nodes in these networks. So, these are some of the important references that one can go through in order to supplement one's understanding of the problem of placement in the topic of coverage and placement in wireless sensor networks. Thank you.